So let's go ahead and solve some practice problems. In this first problem, we're going to solve for pressure. Calculate pressure in kilopascals for 14 grams of nitrogen gas that has a specific volume and a specific temperature. Now, you are told your pressure has to be in kPa, so you can go ahead and figure out your R value right now, which will be 8.314 since that is the value of the gas constant containing kPa in the units for the gas constant. If you look at the other units of the gas constant, you realize that there are some other conditions that you have to have in place. So, for example, your volume has to be in liters. Your given volume, however, is in milliliters. So, we're going to convert this right now to 0.250 liters. Your temperature is given in the problem as 25 degrees Celsius, but as you can see, the unit for temperature is given in Kelvin in the units of the gas constant. So the temperature in Kelvin for 25 degrees Celsius is 298 K. So we have our volume, we have our temperature, we have our R value. We are solving for P. So we need to figure out our N, which is moles, not mass. So 14.0 grams has to be converted. This is going to be 14.0 grams divided by 28.014 grams. So when you cancel out the grams and do your dimensional analysis, you get 0.49975. You actually get a lot more decimals after that, but I would just always, like, as a habit, honestly, just carry more decimals than you would if in the course of solving the problem, and then you can figure out your sig figs later. Don't stress about sig figs in each problem more than once. So now we've got all of our values, and let's go ahead and solve for P. So the original statement of the ideal gas law is this, but since we just need to get P, let's divide both sides by V so that pressure can be isolated on its side of the equal sign. So pressure is equal to N times R times T divided by V. So the number of moles is 0.49975. Our R value is 8.314 liters kPa divided by moles Kelvin. And temperature is 298.0 Kelvin. All of that goes in your numerator. Your denominator will be your volume, and we're going to put 0.250 liters in its place. So hopefully you can see that a lot of units will start to cancel out magically, moles and moles, liters and liters, Kelvin and Kelvin. So we will get an answer in kPa, and you do get a giant answer. That actually kind of makes sense because 250 milliliters is not a big volume, so the pressure is probably enormous. So in my calculator, I get 4,952 point and a bunch of decimals. I have three significant figures from all of my measurements, so I'm going to write this number in scientific notation. So 4.95 times 10 to the third kilopascals for this particular nitrogen gas sample, which is not undergoing change. For this second practice problem, we're going to go ahead and solve for K, or temperature, not K, but it will be in units of K. Therefore, we'll have to convert to Celsius after we get our answer in kelvins. So we have 30 grams of carbon dioxide, so we are going to solve for N. N is 30.0 grams divided by the molar mass of carbon dioxide, which is 44.009. So when we divide, we're going to get under a mole. Uh, 0.6816. I'll put 78 just to cover my bases. So I have the number of moles of carbon dioxide worked out. We know that it's going to be at standard pressure. We're not told what units to use, therefore it doesn't matter. As long as your R value has the corresponding pressure unit, everything will work out. So you can actually choose what standard pressure value you want to use. So let's choose 760 torr for standard pressure, meaning our R value is going to be 62.4 liters times torr divided by moles times K. Finally, I should have told you the volume. That's my mistake. Let's make the volume of this gas just 10.0 liters. So let's go ahead and solve for temperature. P times V equals moles times R times T. So we have to isolate by dividing both sides by N times R. Therefore, temperature is going to be P times V divided by N times R. So pressure is 760. Volume is 10 liters. All over moles is 0.0681678 moles. Times R is 62.4. I'm going to put square brackets around my terms in the denominator simply because I know the yellow calculators require this, and I just want you to try to get more into the habit if you're not already in the habit of putting parentheses around your terms in the denominator. So moles cancel, liters will cancel, torrs cancel. Therefore, we're going to get an answer in Kelvin. So when you work this out in your calculator, you will obtain, I get 179. That is again going to be in Kelvin. To get the temperature in Celsius, you need to subtract 273. So when you subtract 273, you get negative 94, actually 94.3 degrees Celsius. So it's pretty cold, but that's all right. So again, if you run into this kind of issue and you're not told pressure units, as long as you make the pressure and the R units match up, you should be okay. So now let's take a look at a third problem where we're solving for volume, but there are two ways to solve this problem. I will do this first the longer way. The longer way is to use PV equals nRT as a matter of fact. So calculate the volume of 75.0 grams of chlorine gas at STP. So volume is our needed quantity. Pressure, again, it says STP, it doesn't matter. So let's use 1 ATM. Why not? Our volume is our unknown. We need to figure out moles. We have the mass of the gas, so 75.0 grams. We're going to divide by the molar mass of chlorine, which is 70.906. So grams cancel. 75.0 divided by this molar mass will give me 1.0577 moles. We know that it is standard temperature, which is 0 degrees Celsius, but we need Kelvin, right? So this is going to be 273 Kelvin for that. And for our corresponding R value, since we chose 1 ATM for pressure, this is going to be 0.0821 liters times atmospheres divided by moles times Kelvin. So when solving for volume, this is going to be PV is equal to nRT. So if you want volume, that's going to be nRT divided by P. So substitute all of your values that we have just determined. So 1.0577 moles times 0.0821 times 273 divided by pressure is 1 ATM. So Kelvin's cancels, mole cancels, ATMs cancels. We're going to get liters out of this. So volume will be, really in the calculator is 23.70 with a bunch of decimals after it. I did use 1 ATM for my given pressure. However, that is a constant, like uh, it's a quantity that we use. It's a quantity that we use to solve. So let's use our measurement for our significant figures. That's going to be 3. Therefore, 23.7 liters is going to be my answer for the volume. So that's the longer way to solve for this problem. The shorter way and the smarter way, let's be honest, is to understand that this is a gas at STP. So therefore, the relationship 1 mole equals 22.4 liters holds true. So it seems like we can just convert the 75 grams of Cl2 to moles. That's going to be 70.906 grams is our molar mass, as we figured out before, and then multiply by 22.4. And so then when you solve, you will get the same answer. You get 23.7 liters. Um, in a testing situation, definitely you want to use as many quick ways as you possibly can to get to your answers. This is one of them. It's a very nice, handy shortcut. However, again, it only holds true if the problem expressly tells you, or if you're able to infer that the conditions are truly standard temperature and pressure. If they're not, you have to use PV equals nRT, which is always a kind of a solid standby equation that you can always use regardless of the conditions. So if you freeze during a testing situation and you don't remember STP, just remember that you can always use PV equals nRT. By the way, I do want to take a minute here and actually derive 22.4. Like there is actually a way you can prove that. So I'm going to switch inks here because I'm kind of choosing to go off road here. But let's prove 1 mole is 22.4 liters. So that's PV is equal to nRT. So we're going to solve for volume. So when we rearrange the equation, we get nRT divided by P. We're looking at STP, right? So let's just use pressure is 1 atm just for fun. And our temperature is going to be 273 K. Therefore, our R value is going to be 0.0821 liters times atmospheres, et cetera, et cetera. So volume is going to be 1 mole, because after all, it was for 1 mole of any gas. That's the definition of molar volume, times R, 0.0821, times 273, and all of that is over 1. If you solve for volume, you actually get 22.4 liters. So just for interest really, but just to show you that 22.4 liters is a quantity that can actually be proved mathematically. So now let's use the ideal gas law in two different ways. Just for interest really, but just to show you that 22.4 liters is a quantity that can actually be proved mathematically.